Yeah, we can see your screen. Over to you, Sara.
Okay, thank you. Hello, everybody, and welcome to the third session of my talks. In the last two sessions, we tried to understand something about the basic concepts of matroids, and then we chose a geometric point of view to look at some associated polytopes called cycle polytopes. And as I promised before, today we are going to be more algebraic and talk about some algebras and ideals that we associate to matroids. And they are also called cycle algebras and ideals. So first of all, we fix a field, K. And before going to our stuff, I would like to give a more general definition of a polytopic algebra or a special kind of toric algebra. We talked about lattice polytopes. So having any lattice polytope we can inside RD with non-negative coordinates, of course. We can associate an algebra denoted by KP, which is defined to be a monomial algebra over K, generated with some monomials which are in correspondence with the lattice points of my polytope, namely y to the power a and z beside, such that this a belongs to p, the lattice points of my polytope, which is this. Okay, and this algebra is inside this polynomial ring y1 to yd and z, and by this I mean a monomial. Very likely you know that we can write monomials in this short way, but more precisely, this is just y1 to the power a1, y2 a2, and so on, yd ad, and z. And this a is, as you see, it is in z to the power d, so it is a1 to ad. So we write this short form to denote our monomials of this type, and this exponent vector comes from the lattice points of the polytope. So always we can define such an algebra, which is indeed a toric algebra. I mean, a special type of algebras. If you do not know what a toric algebra is, don't worry. I don't want to use the properties that much. And it is also a standard graded. Generated in degree 1. How degree 1? This is induced by taking degree of z equal to 1. So we put this z just to manage the degrees actually. And degree of all yi's equal to 0. Then this algebra KP is generated in degree 1. All the monomials generating monomials are of degree 1, and then we have just a standard graded algebra over K. So this is in general, always we can associate such an algebra to any lattice polytope, but now I want to focus on our objects and apply this structure on our own objects. So You remember that we are working with matroids, so we take any matroid that you like. You know from yesterday that we had a polytope, a card cycle polytope denoted by this notation. So this is a lattice polytope. So in the procedure that I mentioned already above, we can associate this algebra, the toric algebra associated to cycle polytope of M. Just to simplify the notation, I just write K psych M from now on. But more precisely, let us look at this algebra. This K psych M is now generated with some monomials. So my polytope was associated to matroid, and the bridge in between were cycles. Cycles of my matroid were the disjoint union of circuits. So I should consider the characteristic vectors of those cycles, then their convex hull would be the polytope that I'm considering. So now these lattice polytope, lattice points are just associated to cycles, the characteristic vectors. So y to the power c and z, as we agreed above, where c comes from a cycle of a matroid, because they just determined my polytope, the lattice points of my polytope. And this is inside this polynomial ring, sorry, y, e, and z, such that e is inside the ground set of my matroid. Okay. And just to be more precise, let me write again this yc. It was just the multiplication of some variables. Which one? Those which belong to C, which is the cycle of my matroid. Okay, so this is the K algebra that we are considering. We introduced it above in a more general setting, and here for my matroids. But since I'm saying that this is a toric algebra, for those who are a little bit familiar with this concept, now we can represent this algebra by a homomorphism, let us call it phi m, from a polynomial ring Sm. M, I put M because I just want to remind you that we are working with a matroid M. This polynomial ring is over K again, and its indeterminates are in correspondence with cycles of my matroid. So phi m is from this polynomial ring to my algebra, my cycle algebra. So how does it work? Very natural. It sends a variable associated to a cycle like C to the corresponding monomial in the right-hand side, namely y, c, z. And okay, we take these variables to be in degree 1, as usual, standard grading. And as I discussed before, we took also these monomials of degree 1. So this map phi m is a homogeneous homomorphism. And if we look at its kernel, then it would be, again, homogeneous ideal. So kernel of Vm is homogeneous or graded. And if we look at the way that we defined this map, it is clear that this is surjective. For any generators of my K algebra in the right-hand side, we find something in the polynomial ring Sm, which goes to that generator. So this is for sure surjective. And if I take this kernel, then you know from your elementary algebra courses that Sm over this kernel is isomorphic to my cycle algebra. Okay. And now I want to give a name to this ideal, this kernel of phi m. This is indeed called the defining ideal of this algebra. Since this is a toric algebra, we need a defining ideal of K psi m, and we call it the cycle ideal of Matroid M. Okay. So now I have cycle algebra and cycle ideal. So far I associated the algebraic objects that I wanted to my matroid. So just to repeat that isomorphism, we have Sm over I psi m. This is the notation that I would like to use for my cycle ideal, which is exactly the kernel above. This is isomorphic to my K algebra. Okay, and this ideal, this cycle ideal, which is called also a toric ideal, since it is a defining ideal of a toric algebra, it is a prime ideal. Always toric ideals are prime. It is a graded or homogeneous ideal. We just mentioned above, this was just a kernel. And what else? It is also generated by some special types of polynomials, which are interesting enough in the literature. So generated by the so-called pure homogeneous binomials. So by pure homogeneous binomials, we mean binomials of this type. So binomial is just the subtraction of two monomials, maybe with some scalar multiplication. But when we say pure, there is nothing, just two monomials like this. And look at here, my kernel, my cycle ideal lies in this polynomial ring. So it should be written in terms of these variables xc, where c is a cycle. So just a typical generator would be xci, I from 1 to some d, minus multiplication of x, let's say di, I from 1 to d again, because I'm saying homogeneous here. So it is clear the subtraction of two monomials, so I see binomial. And I said pure means that there is nothing, no alpha, for example, here or beta here. So this is also binomial, but when we say pure, we do not have something like this here. So this is a typical generator of such ideal. We have this information, it is good. We have something in hand to work with these ideas, but this is very little. So we would like to understand this ideal and this algebra a little bit more. Okay. And just don't forget that these Ci and Di were just cycles of my matroid. Okay, I think now is the time to look at an example. As a first example, I would like to look at a familiar example that we saw yesterday, this small graph P3, the path over 3 vertices with edges labeled by 1 and 2. If you remember from yesterday, we investigated its cycles. So the cycles were just, okay, we always put empty set inside. Okay, since we saw the example yesterday, I didn't write, but maybe it's better to write that my M here is the co-graphic matroid. And in co-graphic matroid, again, if you remember, we said that the circuits are just minimal edge cuts. So it means that 1 was one of them, 2 was the other one. And since I'm talking about cycles, I can take this joint union. So we had also 1, 2. We saw this example precisely yesterday. So this is the set of cycles. And now I want to associate my algebra, K psych M. So over K generated by these monomials. So I put Z here because I'm associating to this empty set, because I should put Y to the power C, the cycle. And since I have just the characteristic vector of empty set is just 0, 0, 0, so I do not put Y. Okay. And then, okay, for 1, again, Z I have here, but which monomial I should write? I have just one element from the ground set. So I put Y1 to Z, Y1Z, and for 2, Y2Z. And finally, for 1, 2, I have the monomial Y1, Y2Z. And this is inside this polynomial ring, Y1, Y2, and Z. So this is my K algebra. And as you see, I just use this correspondence. So I have the cycle algebra in this way from the definition. And if we want to look at the map that I introduced above, it was phi m from SM. Okay, the indeterminates of SM were coming from the cycles of the polytope, of the matroid. So here I have K. Okay, you see cycles here. So what I put here, I put X empty, X1, X2, X12. I just write the same names just to have a better feeling maybe. Okay, to my algebra, I write my algebra again precisely here, Z, Y1Z, Y2Z, Y1, Y2Z. And we saw that this map works in this way. It sends the indeterminate attached to one cycle to the corresponding monomial. So X empty comes from empty cycle. So it is sent to Z, X1 to Y1Z, X2 to Y2Z, and finally x1, 2 to y1, y2, z. So this is also the homomorphism phi m. And for the cycle ideal, we need to compute the kernel of this map. For the moment, let us see if we see a candidate of an element of the kernel. So if we look at x empty, x12 minus x1, x2. This element is inside Sm, and by phi m goes to what? Okay, x empty goes to z, x12 goes to y1, y2z, minus x1 goes to y1z, x2 goes to y2z. So they are equal, right? y1, y2z squared are both. So this is 0. So for the moment, at least we have an element inside the kernel, but the kernel was just our cycle ideal of matroid M. Okay, you can work a little bit. It's not so difficult here to see what is exactly the kernel, but it needs a little bit work. But now at least I can tell you that you can see here that this cycle ideal is just generated by this element. So it is a principal ideal generated by this pure homogeneous binomial of degree 2. In general, computing such kernels or cycle ideals is not so easy. I mean, it's not easy. And for small examples, you can use computer. You can also give this example to Macaulay 2, for example, and it will compute for you the kernel. But in some small examples, we can also work a little bit with the grading and the properties that we know. And we get some generators, but in general, it can be a tough job. But here you can believe me that this is the cycle ideal, and you can check it later. Okay, when we have this algebra and this ideal, we may ask about the height of this ideal or the crude dimension of the algebra. Since this is an easy ideal, a prime ideal, which is also principal, so you can easily understand that the height of this ideal in this example is just 1. And then you can also easily compute what is the crude dimension of the cycle polytope, again, in this example, because this algebra was isomorphic to the quotient of Sm over the cycle ideal. And for an ideal in any polynomial ring, let's say K T1 to Tr, you know this height dimension formula, that height of the ideal plus dimension of R, what I gives you R, small r. So in this way, since our polynomial ring in the left-hand side has 4 variables, and I obtained the height of the ideal equal to 1, then this dimension would be 3. Okay. But this was just in our example. What can we say in general? So here is a good news that we can say something in general, because our algebras are coming from polytopes, lattice polytopes. And in general, if you know the dimension of the polytope, you can compute the crude dimension of the associated algebra in the way that we associated. So it will be the dimension of the polytope plus 1. You can see it in several books that are talking about toric algebras coming from polytopes. But if we look at our case, we know something about the dimension of the polytope. Last session we saw there was a formula that dimension of our cycle polytope was the number of co-parallel classes of M. I don't want to repeat this word, this expression always. I just denote it by D of M from now on. So from what I claimed, that is proved, then the dimension of the cycle algebra would be dm plus 1. Okay, so we have this formula now, and hence again with this familiar formula, we know that height of the cycle ideal would be, okay, again, let's go back to this map, SM. The number of variables are the cardinality of set of cycles. So we have cycles as many as the variables of SM. So now just applying this height dimension formula, I get the number of the cardinality of cyc M, or the number of cycles, minus dm minus 1. So we also have this formula for height. Okay. So we have these formulas in general, and to understand better the ideal, the first question would be when this ideal is 0, when this kernel is just 0. Let's see when this happens. It is a very easy lemma that I'm just writing here. If we assume that M is a matroid, then the following are equivalent. 1, what I said, this ideal is 0. And 2, dm equals the number of cycles minus 1. And for this purpose, we only need to look at this height formula, because my ideal, my cycle ideal, as I mentioned before, is just a prime ideal. So since this is a prime ideal, then we know that this is 0 if and only if its height is 0. So it is an easy observation. So then with this observation, let's look back at the formula of height. I mean, being 0 means that height should be 0. Height equal to 0 means exactly this 2. So as I said, this is a This is an easy lemma, but again, now we have, based on our formulas and what we mentioned yesterday, we have a totally combinatorial criterion for vanishing of this ideal. Okay, but still, this DM, computing this DM, is not so easy in matroids. So we would like to try some cases that we can see this DM better from my matroid. So I want to make this more clear from the matroid. And for this, I would like to look at matroids with a certain property that one of the participants yesterday also asked if they play some role in the literature, if they are important at all. And I said, yes, maybe we today we can talk about them. And that is the moment that I want to do this. So a matroid is said to be simple if it has no loops and no non-trivial parallel classes. If you remember again from yesterday, trivial parallel classes were those which are just singletons. And we had an example with this property, and that's why one of the participants asked this question, this good question. So simple means no loop, no non-trivial parallel class. It means that all parallel classes are just singletons. And if I say co-simple, it means that there is no co-loops. You know, when I put co before the word, it means that I'm looking at the dual matroid. And here, no non-trivial co-parallel classes. So now we have two new concepts, simple and co-simple. And right now, I want to repeat this lemma, the above lemma, to have a criterion for vanishing of this ideal, but not for any matroid, because I was interested in having this DM more readable from the matroid. So I repeat this lemma for co-simple matroids. So as a corollary, if M is a co-simple matroid, then the following are equivalent. One, okay, the same as before, this ideal is just 0. But 2, in the left-hand side, we have just the cardinality of the ground set. So it is much better than the number of co-parallel classes or whatsoever we had above. So this should be the cardinality of psi -1. So let's see why. Because when I say co-simple, by definition above means there is no co-loop and no non-trivial co-parallel classes. Okay. So it means that for any element of the matroid, this set is not a loop because we don't have any a loop of a dual, I mean, because of the definition of co-simpleness. Then maybe write a co-loop really. And this gives us that any such set is a co-parallel class of M. And not only this, but also these are the only co-parallel classes of M, because these are trivial ones. And by co-simple, we mean that there is no non-trivial. So, and they are the only co-parallel classes. Okay. If you just forgot these expressions, it doesn't matter. Don't worry. You can later check what we said yesterday. Just consider that under some conditions, we could make the formula a little bit better, more than a little bit really. So, and then, okay, how many coparallel classes do I have now? For any element of E, I have one, and these are the only ones. So this means that the number of coparallel classes, which we denoted above by dm, is just the number of elements of the ground set. Then if we look back at our lemma, okay, I'm just replacing this yellow part dm by cardinality of E, sorry. So that's all. So for co-simple matroids, which are a big class of matroids and many interesting matroids are inside them, we can achieve for the moment that when the cycle ideal is just 0. Okay. We saw this example of P3 yesterday. Maybe I just draw it again. And we worked with mg star. And if you remember there, the only coparallel classes were just 1 and 2. Yeah, and this was co-simple. That's, I mean, this was the moment that I was asked by one of you about such a nice class of matroids. Okay, so mg star is co-simple, so we are allowed to use this corollary for it. We computed the ideal above. It was a principal non-zero ideal. So 1 does not hold for MP star. So 2 should not hold as well. And we know that the cardinality of E for this matroid is just 2. But just a few minutes ago, we recalled that the number of cycles were 4 minus 1. So this equality does not hold, just to check our criteria. Okay. Now that we are talking about vanishing of this ideal, it's maybe interesting to say that in general, in the case of co-graphic matroids for any graph G, if you take the, let me write M, the cycle algebra and cycle ideal of this guy is rarely 0. Indeed, this is the case if and only if your graph is just an edge or a triangle. But this is just for the co-graphic matroid, which we obtained it in the first paper by Tim Romer when we were working with cut polytopes, and the base object was co-graphic matroids. But in general, as you see, okay, this criteria should be checked for several classes. And now I want to give you another example, not graphic or co-graphic. And this example is, again, one of the very famous examples in matroid theory, phonomatroid and its dual. So, as denoted by F7, and dual, of course, F7 star. I need always a ground set, and the ground set here is 1, 2, 7. And the basis of F7 itself are all 3 subsets of these 7 elements, except some that I will tell you. So all 3 subsets of E, except, if I just can show you, okay. Picture here in a moment. Okay. Except those 3 subsets that you see in this picture on the lines, different lines you see here, 6 lines, and 1 curve, the circle in between, except what you see in the picture. By picture, I mean 1, 6, 2. This is not a basis. 1, 5, 3, 2, 4, 3, 1, 7, 4, 4, 6, 5. So you see 4 lines and 1 curve inside. These 3 subsets are excluded, but the rest are bases of my phonomatroid. And considering these bases, and for sure you get all the independences because all subsets of these 3 subsets are independent. So it's easy to obtain also the circuits, minimal dependent sets. You can easily observe that the 3 subsets.
Sorry, by circle you mean 5, 6 are connected, and 6, 4, and 4, 5 are connected too?
By the cycle, you mean in the
by
figure?
The circle
you
inside. Yeah.
Yeah, 4, 5, 6. The one around.
Yeah. Okay.
The 3 elements around the cycle. Yeah. And on the line, I mean 1, 5, 3, for example. The things that they are just located on that line or curve. Okay. So the ones shown in the picture are not independent sets because we just excluded them. So they are dependent sets, and you can see that they are minimal ones. So they are inside my circuit set. I denote these 7, 3 subsets of the figure C1, C2 to C7, no matter how you just name them. Just I want them to have a name. So CI, the ones in the picture, and their complements. So I have a ground set E. I have a basis B, which was consisting of all 3 subsets of E, except the 7 3 subsets shown in the picture. So you can easily check, but you need to check really, that the circuits are these three element subsets of the picture together with their complements, E minus each of them. So they are circuits. Having circuits, for sure, you can also compute cycles and everything else. But for the moment, that's enough for me. Just I want to verify two things. That here inside this set, you don't see any loops where circuits of cardinality 1. What you see here are of cardinality 3, and their complements are of cardinality 4. So no loops for sure. And no non-trivial parallel classes. Because if you want to have a non-trivial parallel class, by definition of yesterday, you need at least two parallel elements. Two elements which together provide a circuit. But here circuits are of cardinality more than 2. So no non-trivial parallel class. But just a few minutes ago, we saw that these two properties give a name to my matroid. So this phonomatroid F7 is a simple matroid. When F7 is simple, it means that F7 star, its dual, is for sure co-simple. We were interested in co-simple ones because we could read this formula in a better way. When we had co-simpleness, this was something much, much better to see, to compute. And then we could judge if our ideal is 0 or not. So that's why I am working with something which is co-simple now, but a new matroid. I didn't want to work with the previous matroids that you know them very well, hopefully so far. So this F7 star is co-simple, and the cardinality of its ground set, which is again E, is 7. By our formula, what I need to compute is the number of cycles. To see what are the cycles of this matroid, I need to see what are the circuits, and then I take this joint union. You can see that the circuits of this F7 star, so, but I mean, somehow I'm putting it as an exercise for you, but it is just some combinatorial games. You can see that they are just the complements of what you see in the picture. Some 4 elements subsets. They were also here. They also appeared there. But here, these are the only. Sorry?
They are 21. They are 21 in total?
No, here in a C of F7 star, they are just 7. Because you have...
but when you define the base of F7, so you excluded them among all the 3 subset of...
Yes. BF7 has, 3 choose 7, 7 choose 3, minus 7 elements, minus
their
7.
complement, and then 14 will be taken out, so it will be in total.
No, B7 has a lot of elements, but when I go to C and circuits here, I'm just taking as by CIs, I mean the ones that you see in the picture, not all 3 subsets that we considered in BF7. We just see 7 3 elements subsets in the picture and their complements. So 14 elements
14
inside.
Yeah,
exactly here. And for the dual, which I put it as an exercise, here we have just 7 elements because you can see that just complements remain here.
Yeah, okay. Okay.
7, yeah, 7 sets of cardinality 4. So this is not difficult, but I just want to save the time. And cycles were disjoint union of circuits. And always we put the empty set here. But then, since I have 7 elements, and this circuit set, all elements are of cardinality 4. No pair of them could be disjoint for sure. So the only disjoint unions could be trivial disjoint unions just by one of these. So I just have the circuits themselves together with the empty set, and I cannot take any disjoint union of them. So now the cardinality of this cycle F7 star is just 7 here, 1 here, 8. So as a summary, now I have a co-simple matroid. Its ground set has 7 elements. The number of cycles is 8. And if I just go back to the formula, too much. Okay. Here. Oh, I'm sorry. Okay. And here, what you see says that in the left-hand side, we have 7 in our example, and in the right-hand side, we have also 7. So 2 holds. Consequently, 1 should hold. And with this criteria, we can deduce that the cycle ideal of F7 star is just 0. So we didn't compute the kernel itself, but together with what we had, we could obtain a criterion to check whether this is 0 or not. And the matroid is not trivial at all. If you want to work with that map and the algebra itself, it needs some work really. But our criterion can show that this ideal is 0. And as I mentioned before, in the special case of co-graphic matroids, the ideal is rarely 0 in just 2 cases of the graph, just an edge and a triangle. But this example shows that in general for any matroid, even in the case of co-simple matroids, there are more interesting matroids, non-trivial matroids, which give us 0 ideal. Okay, so having a complete list of them would be interesting if somebody can achieve, or yeah, at least some lists would be nice based on this criterion. Okay, and now that we understand about vanishing of the ideal a little bit, at least we have a criterion, we can ask about more things. I mean, what can we say about the generators? If it is non-zero, what we can say about the generators, about the degrees of them? Can we have some linear forms, homogeneous polynomials of degree 1 inside, which are the ones which are generated in degree 2, and so on? Okay, so still there are a lot of questions remained, and for this purpose, I would like to fix a notation. First of all, we denote the highest degree of a homogeneous generator in a minimal generating set of I psi m. So I have a matroid, I provide the cycle ideal. If it is non-zero, it has some generators. Since it is graded, it has a minimal homogeneous generating set. They have probably different degrees. We denote the highest degree appeared among them by mu of m. And studying this for a special class of matroids, namely co-graphic matroids, was initiated by Strumfels and Sullivan in one of the papers that they list some conjectures there, and there are also some conjectures regarding this invariant. And this was a motivation of our study as well. If we have enough time in the next session, I will tell you more about it. But for the moment, I would like to say at least something about this invariant. We go a little bit further now, another lemma. Again, M is a matroid. Then, first of all, as I said, I'm interested to see if it is non-zero. I mean, do I get some generators in degree 1? So I would like to look at degree 1 homogeneous component of this guy, which I'm claiming here that it is 0. And consequently, if the ideal is non-zero, then we can deduce that mu is bigger than or equal to 2. I mean, having 1, if you prove 1, and if the ideal is not 0, then it means that the degree of the generators should be at least 2. So, and the highest one should be at least 2. But to observe the first one, what happens if I want to have a linear form inside? If you remember, we said that the generators of this ideal are pure homogeneous binomials. And now if I want to take a pure homogeneous binomial of degree 1 in SM, whose indeterminates came from cycles, we have some binomial like this. There's no multiplication behind because I just want degree 1, where C and D are cycles and distinct. If this is inside the ideal, we don't forget that our ideal was just kernel. It means that its image should be 0. But what is phi of this element? This is just phi m of xc minus phi m of xd. And if you remember, our map sends these two guys to certain monomials. So here we what we get is multiplication of ye, where e comes from c, z minus, and this is just 0, minus multiplication of ye from d, z. And when this is 0, of course, z's do not have anything to do. And it means that the characteristic vectors of C and D are the same. And it means that C and D as sets are the same, but they were distinct because I wanted to have something non-zero in my kernel. So this is impossible to have linear forms inside the kernel. That's why this degree is 0. And I mentioned before that why this happens. And I think now I should stop because of the time, but later we continue with this invariant mu m, maybe tomorrow. And we even go a little bit further to see which kind of tools can help us to attack, to understand better this invariant and some other related invariants like Bell numbers and so on. Yeah, I think then I would stop here now for today.
Thank you, Sara. Thank you very much. Are there any questions from the audience side? There's nothing in the chat box. Anyways, you clarify everything with the elaborative examples. So I think everything is clear and seemingly well arranged and interesting. So there is a remark in the chat box. So it
Yes,
was
I
very
saw
well
it.
organized. Thank you very much, Sarah, and sorry for the inconvenience due to the internet disconnectivity in the beginning of your
No,
lecture.
no problem.
Okay,
Thank you for
thank you
your
very much.
attention. And
Sarah, it would be
see you
appropriate,
tomorrow.
Sarah, it would be appropriate if you can mention that reference for the participant if someone would like to read the paper of Schrumpfels and probably your paper with Tim Romer before coming to the next lecture for the participant beforehand.
Yes. Yeah. So first of all, for knowing more about matroids, I mean, somebody also wrote an email to me, and I also mentioned this reference that for knowing about matroids better, you can see the book of Matroid Theory by Oxley, which is a really good reference for matroid theory. And about MUM, if you want to know the origin of such problems, you can see the paper by Schrumpfels and Sullivan. I think this is something like toric geometry of, I hope I'm right, toric geometry of cuts. I think I have somewhere open. Maybe that would be great if I have. Yeah, I can show then. You can see, right?
We can't. You shared only the screen, I think. The
Oh,
best.
I should change the screen now. Okay, at least I myself can check the name, toric geometry of cuts and splits. Okay, I just write it down there. Of cuts and splits. So I was right so far. This is one paper, somehow the motivation of our works. And then I cheat again. Let me see here. And there's two papers by Tim Romer and myself. One is, and it has been published in European Journal of Combinatorics. It is retracts and what happens here? Retracts and algebraic properties of cut algebras. And maybe the last one, cycle algebras and polytopes of matroids. So these two are by Tim Romer and myself. The first one, as I said, has been appeared in European Journal of Combinatorics. And the second one is just online on arXiv. The first one you can also see on arXiv. Yeah, and about cuts and splits, there are also some books, but I think about what I'm talking about, they may suffice.
Yeah, thank you, Sarah.
Okay.
Thank you very much. All these papers are available on arXiv if someone would like to download, so they can download from there. Thank you, Sarah.
Exactly.
Thank you very much. Thank you. Sarah has the last lecture. Yeah, Sarah has the last lecture on Friday, I think now.
Friday, yeah.
Yeah.
Yes,
On Friday.
I mean, I made a mistake. I said tomorrow. Yeah, Friday. Yeah.
Yeah, right. It's Friday, final lecture. So we'll see you on Friday. Thank you. Thank you very much.
Yeah, thank you, and see you everybody. Bye.
Bye.